connection. Anyways, I don't know. We will see. Yeah, it's uploaded because of the size. Anyways, okay. So as I've been introduced, my name is Emre Ergin, and today I will be presenting our paper called Robotic IoT-Enabled Windy Line Scan Integration for 3D Point Cloud Data Processing. Myself, Dr. Sven Stumm, and Professor Sigrid Brell-Cokcan, we are coming from the Chair of Individualized Production in Architecture in RWTH University, Germany. So further ado, let me start with the introduction and motivation. So as we know, as we have seen throughout the conference, there is a demand of aligning the digital model to physical model, because whatever you plan and test on simulation or the digital level, it's never accurate when you apply it on on-site or off-site construction. So that's one of the big things. Secondly, the highly dynamic nature of construction sites requires some sort of adaptability or modularity, because also at the research level, also in the application level, the locations, the environment changes a lot constantly. So there's a need of like a modular approach or like reconfigurability approach for different kind of automation solutions. And finally, for the scope of this project, I mean, it's a bigger project, but for the scope of this paper, we had the need of, so we are dealing with steel beam manufacturing, so like some truss manufacturing through welding and assembly. We needed some sort of near field inspection methodology for geometrical inspection, more or less. So for that reason, for our paper, we wanted to integrate a laser profiler on an industrial robotic arm, and wanted to utilize MQTT-based connection for the local network, partially cloud network, and also utilize not too complicated off-the-shelf point cloud processing algorithms, which are openly available, to be able to make sense of this data and somehow apply it in our use case. Okay, so in total, now I will go through these four methodologies that at the end become the product itself. First, the physical integration. So I was talking about this robotic arm integrated on a laser profiler. The first thing you do when you put a laser tool on a robot is, as you know, to calibrate its tool center point. If you know, the traditional 4-point calibration method works, when, especially works very well if you have a physical point. But in terms of laser scanner, we struggle that, as you can see on the first image, that even though this laser profiler is meant for like on conveyor belts, which is meant for like some very detailed electronics and very high precision, has very high precision, it was unable to detect those spike of the calibration point. So calibration reference. For that reason, we proposed a way that we iteratively calibrated the TCP based on a reflective marker that we are getting the data from illuminance value of the line scanner. So that's the first part. And after this, actually, we had a calibration rate of like 0.18 millimeters of deviation, which is reasonable, but you will see some problems we had afterwards. Next, so I talk about this modularity. So if you want to use a end effector with a robot, a motion system, usually the way you interface is through the robot controller itself. So there are some like interfaces you have to talk to the integrators, or there are some like you have to talk to the end effector if you are build end effector vendor or the robot vendor and things like that. What we are doing is that first we are using cloud remote control. That's an extension of plugin KUKA PRC. Maybe you are aware of it. And this enables us to connect the robot controller itself to a PC or Raspberry Pi to be able to send more human readable data, to be able to, through MQTT, to be able to make some motions available. The other way around is that we are getting a constant state data of where the tool center point is in terms of transformation, as well as the speed of the current TCP and things like that. So currently we are getting this state to the local MQTT broker. This is from and we can say that this robot is now an IoT-enabled device that is standalone and just working by itself. Not by itself, but existing in the workcell environment by itself. Additionally, the laser profiler. So for that, we develop a different script, let's say, that is direct on a Raspberry Pi as well, that is directly connected to, like, physically connected to Raspberry Pi itself, but then we made it in a way that it's an IoT device and always publishes this sensorial data. So now we have transformation data, we have a sensorial data. What do we do? To make sense of this sensor data, we combine them together. And for that reason, then the next step of this modularity is a service. So we had a actuator, we had a sensor, and now we have to make sense of it in 3D space. For that reason, we used a standalone different Dockerized containerized service, which takes the transformation data, sensorial data, combines them in 3D space so that we can make sense of this three-dimensional data and like save it iteratively to be able to get a 3D point cloud from a like single line scanner sensor. For that synchronization, we also use like network time protocol timestamping. This is we have our own university has our own network time protocol server where we can correlate this data based on some differences, because when you never, especially in the network conditions, you never know when you get the sensorial data and when at what timestamp this robot positions itself. So this is a way of doing it. And at the end, for example, here, talking about line scanners, they have laser profilers. They have high precision, but in terms of losing some of the coverage, as you can see, for example, for this example, steel beam edge connection, we had to, for example, scan 4 times, and then you can see that they are more or less registered to each other, and at the end, we just apply the meshing algorithm to see if it makes sense. So, okay, I will skip this video because I will explain it afterwards. It says something here that I can't. Yeah, it's okay. I will just skip it. And I talked about our methodologies, and after some couple of, do I have, okay. After some couple of tests, we have seen that this small deviation in the tool calibration methodology had some effects on the final results, even that was not visible by a human eye. We see that after close inspection, for example, on the figure 8, this figure, you can see that if they are not registered and just like scanned as they are, there's some like inconsistency in the surface of the geometry itself. For that reason, we wanted to implement iterative multi-waypoint cloud registration methodology, and that is from Open3D. I am aware that you are familiar with Open3D. It's open source point cloud or geometric processing library. And the results, as you can see that here you see, I think 6 different scans unregistered. And this is the deviation comparison to the real model that has been scanned with a handheld scanner, which took like 30 minutes or so. This was just this whole scanning took like, I think like 3 minutes or so. And on the right, you can see that when it is registered, the deviation is slightly bit lower. The reason we are having probably the deviation is that since each point clouds are registered to the first point cloud, you can't ensure as well that the first point cloud is relative to the base of the correct position. So, but still, we have seen that this small rate of deviation is workable around. And as you can see from the point cloud, we have detected the edges using neighboring eigenvalue clustering. And at the end, using density-based clustering algorithm, we were able to detect the edges. And next part would be the previous video, but I think I can't play it, but it would show how the scanning procedure works. It's just robot has the line scanner and a welder attached on it. First, an approximate position of the joint is given. It has been scanned. After the scanning, so relative to the robot base, the edges are extracted. Then after the tool change, the physical tool physically welded will be on the robot. And it will just go there, weld it, and retract back. Then also there's like one more pass for like quality inspection. If you're interested, I can show it afterwards, because currently I can't, due to the internet connection issues. And at the end, as I told you, we were, for the scope of the